Hi folks, today we're going to learn about centripetal acceleration, which has to do with circles. So first we're going to see that circular motion is different, and then we're going to learn what centripetal acceleration, easy for me to say, what it actually is. Then we'll see the equation that we can use to calculate centripetal acceleration, and finally we'll talk in general terms about projectiles and a thing called Newton's mountain. So first off, circular motion is different. This is a thought experiment that Isaac Newton did. And he was never really able to explain it entirely. Not that he couldn't, it's just that he never really got to it. But anyway, you learned at the start of this class that all motion is relative and that motion is meaningless unless you're talking about two objects, that one object cannot move all by itself. It can only move relative to something else, which is all very nice. But let's consider for a moment a bucket with water in it. And the bucket is just hanging from a string, and it's not spinning or anything. Everything's still, and the water level is level within the bucket. Now we start to spin the bucket horizontally, so like a top. So the bucket initially starts sliding around the water because the sides of the bucket are fairly smooth. So the bucket is rotating, but the water is not, and the water is still flat. Now, as the bucket spins for a while, then the water starts to spin with the bucket, and it will start to climb up the sides of the bucket a little bit, and the surface of the water will become more bowl-shaped because the water is spinning. And then finally, if we then stop the bucket from spinning, the water inside the bucket keeps on spinning, and the surface of the water is still bowl-shaped. Okay? So those are the four situations. Now, when we think about it, when we start, there is no relative motion between the bucket and the water is flat. And in the third situation, where the bucket is spinning and the water is spinning with it, there is no relative motion between the water and the bucket, and yet the water is bowl-shaped. So we have this weird thing where in one case, there's no relative motion and the water is flat. And in the other case, there is relative motion and the water is bowl-shaped. So what this means is that spinning, rotation, circular motion is something in itself. Something can be spinning without being spinning relative to anything else. Spinning, rotation, is an absolute thing. You can look at the surface of the water, and by the way it's behaving, you can determine whether it is rotating or not, regardless of what else is around. This is kind of strange. It implies that there's something fundamentally different about rotational motion than there is about linear motion. That's the short version of it. Now, this book introduces bits of rotational motion in pieces as we go through the chapters, rather than throwing you all the circular stuff in one chunk. And I like that, so I'm going to be introducing a little bit of rotational concepts right now. And I'll be throwing in rotational concepts in subsequent oncoming chapters, so you get it a little bit at a time. So today our topic is centripetal acceleration. And this word centripetal means center seeking, if you go into Greek or Latin, I forget which one. But it's an acceleration which causes things to curve. And center seeking means that the acceleration is always toward the center of a circle. So here we have a circle, and this is the path that something is taking, like a car, for example, that's driving around in a circle. And at this moment here, over in the 3 o'clock position, at that moment, the car is driving directly north. The vector, the velocity vector at that moment is straight up. Now, as it goes around the curve a little bit later, it's going more northeast because it has a centripetal acceleration, which has caused it to change direction. Even though its speed has not changed, its direction has changed, which means that its velocity has changed. Now, if we compare these vectors, this vertical one is the initial vector, this diagonal one is the second vector. So this is the original vector, this is the final vector, the original velocity and the final velocity. We can see that the velocity has changed. I'm just going to go to the next slide here. The velocity has changed in this direction, which is toward the center of the circle. Now, this is all described on page 70, and I do recommend that you look at it, but here's the short version. Acceleration is defined as a change in velocity. A change in velocity is defined as the final value minus the initial value. This is the final value, this vector here. That's the final value. This is the initial value. That's this vector here. And if you subtract the initial vector from the final vector, this is what you get. That's the change in velocity, which by definition is the acceleration. Another way to look at this is you can take the change in velocity plus the initial velocity, and you get the final velocity. So it's a little vector addition here. The point of all this is that centripetal acceleration is what causes something to follow a circular path. And the acceleration is always directed toward the middle of the circle. Okay, moving on to the equation here. I'm going to have to go through this fairly quickly, so you may want to pause this so you can write this stuff down. A sub c is centripetal acceleration. A is acceleration, the subscript c stands for centripetal. So we can hang a number on this, and like all accelerations, the units are going to be in meters per second squared. And A sub c is equal to v squared over r. This, by the way, is on your AP gouge. This is one of the equations that you get when you're doing tests. V is the tangential velocity, which means the speed of the car as it is going around and around the circle. It's what the speedometer would say as the car is driving around this circular path. Okay, it's in meters per second, and we square that value. And then r is the radius of the circle that the car is driving around. So A sub c equals v squared over r. The units work out. Meters per squared times meters equals meters per second squared. Let's do an example of this. Let's see. So let's go to a piece of scratch paper. There we go. All right, so let's imagine we have a, you know what? I'm just going to use this. This will be fine. No, I'm not. I'm going to do a simpler one first. Okay, let's do that car we had. Car, we're going to say it was moving at 6 meters per second. And we're going to say that the radius of the track was 30 meters. Okay, so that's the path of the car going around in a circle. This is 30 meters. That's the radius of the circle, and the tangential velocity is 6 meters per second. And we want to find A sub c, the centripetal acceleration. So A sub c equals v squared over r. So A sub c equals 6 meters per second. We're going to quantity square that, and we're going to divide that by the radius. So 1 over 30 meters. And when we put all this together, we get 6 squared is 36 divided by 30 is equal to 1.2. 1.2 meters per second squared is the centripetal acceleration. And if they ask you what direction is that acceleration, the direction of the acceleration is always toward the center of the circle. That's how it works. Okay. By definition, centripetal acceleration is always toward the center of the circle. All right, let's do one that's slightly more complicated. Here we are. We're going to have a ball on a string. So I've got a ball on a string, and I'm just going to spin it around and around in a circle. And we're going to say that the string is 0.75 meters long, and that I spin the thing around 100 times per minute, 100 RPMs. And what we want to figure out is the centripetal acceleration that that ball is experiencing. Okay, these are the equations that we're going to use. Again, pause this if you need to. But we need this one to figure out the radius of the circle. We need this one to figure out the tangential speed of the ball. And then here's our equation for centripetal acceleration here. Okay, so if we want to find this tangential speed of the ball, because we need that for v squared over r, v is equal to d over t. But the distance is the circumference of the circle. So that is going to be pi times the radius, 0.75 meters squared, and that equals 0.75 x squared times pi equals 1.77 meters. That is the circumference. That equals d, the distance around the circle. Now, the time depends on, we can do, well, 100 RPM. So we want this to be in seconds. So let's see. 60 seconds per minute times 100 rotations per minute, 100 RPM. So that's going to be 60 divided by 100 equals 0.6 seconds per rotation. Okay, minutes cancel, seconds per rotation. Okay, and that's useful too. So now when we find our velocity, tangential velocity, it is the distance, which is 1.77 meters divided by 0.6 seconds, which equals 2.95 meters per second. That is equal to the tangential velocity. Now we have everything we need to feed this equation. So centripetal acceleration is equal to v squared over r, which equals to 2.95 meters per second, quantity squared, times 1 over the radius, which is 0.75 meters. Right, so 2.95, we're going to square that. We're going to divide it by 0.75, and we get 11.6 meters per second squared. And that's our answer, 11.6 meters per second squared. It's the centripetal acceleration under these conditions. Okay, now let's go back to a thing called Newton's mountain. Here we go. This is a thought experiment that Isaac Newton himself did. And this combines circular motion with projectiles. We've been studying projectiles. Newton said, what if we stand on a tall mountain and we throw a projectile horizontally? It is going to fall to the earth. No surprise there. But what if we throw it faster? If we do that, it's going to go farther before it hits the earth. And if we throw it even faster than that, it's going to go even farther before it hits the earth. But the gravity eventually is continually pulling it toward itself, and eventually the projectile hits it. But Newton said, well, what if we kick it fast enough so that as it falls, it keeps on missing the earth? In other words, this is a projectile. It is falling, just like the projectiles we've been studying all along here, but it's going so fast sideways that the curvature of the earth means that the projectile keeps on missing. And if this happens, then the projectile will go all the way around and come right back to where it started again. And as you may have recognized, this is a satellite. So a satellite is a projectile which is in free fall. It is falling under the influence of gravity, but it's going so fast that it keeps on missing the earth, and it goes around and around and around, and it falls forever without ever hitting the ground. Now, close to the surface of the earth, this won't work because there's air resistance. It will slow down the projectile and it will hit the earth. But if you get above the atmosphere, you go up 100 miles, 150, 200 miles, there's not enough air to slow it down significantly. And if you get it moving horizontally, it will go fast enough to miss the earth and maintain a constant orbit. Okay, so a problem here, a question here is to figure out, well, how fast do you have to be going to maintain that orbit? And I'm going to pause the video right here.